Okay, so let's resume with the next talk of the morning. We have Konstantin Recke from Oxford, and he'll be telling us about dense and sparse, unique infinite clusters in Kazhdan groups. All yours.
So thank you very much for the introduction, and thanks to the organizers for inviting me to give this talk. It's a pleasure to be here. And today I will speak about two probabilistic results about groups with property T, which are based on two joint works. So one is a joint work with Chiranjit Mukherjee from 2023. And the other one is joint with Jan Breivik from this year. So the title may not make sense to all of you right now, so I want to start with some outline of what I'm interested in. So roughly, I want to understand the following question. So understand the interplay between two sides. So on the left-hand side, I will put the geometry of some space. And in today's talk, the spaces will be Cayley graphs of infinite groups, and some Riemannian symmetric spaces will appear. And then I want to understand the, say, behavior of some natural probabilistic or stochastic processes defined on that space. And in my talk today, those will be the so-called percolation processes. And I will define these now very quickly and then get to the results. All right, so percolation. So for the first roughly half of the talk, we'll consider the following setting. So gamma will be a finitely generated infinite group. And okay, maybe breaking a bit with common notation, for me, G will be one of its Cayley graphs. Let's say with respect to some finite symmetric generating set. I should write this. And for the properties I will be interested in today, this may not be always a priori obvious, but these will be large-scale features, so it will not depend on what kind of generating set I choose. And I'm interested in the following stochastic models. So a bond percolation on G is something very simple. So it's a probability measure on subsets of edges. Okay. Equivalently, it's a random subset of edges, but I want to think about it as a random subgraph. So let's write equivalently. It is a random subgraph, which I will usually denote omega, which is obtained by randomly choosing which edges to keep or which edges to delete. So obtained by deleting some edges. Okay? And I will call such a bond percolation invariant if this measure is invariant under shifts. So if I translate my random graph by some group element, then I get the same distribution. Okay? So these will be the main models I'm interested in. Similarly, let me add this here. So we could also, it's also interesting to look at so-called side percolations, where instead of removing edges, so it's the same definition, but instead of removing edges, we remove vertices. So it's the same thing, but for subsets of vertices. All right, so So maybe as a warm-up, let's look at some examples which we would be interested in. So the main example is so-called Bernoulli bond percolation. Bernoulli bond percolation. Which has a parameter p between 0 and 1. And it just does the following. So think of some plain graph. And then at each edge, you just throw a coin to decide whether to keep it or delete it independently. Right? So in this notation, it would correspond to a measure, which is just a product measure over all edges. And then probability p, you keep the edge. And with probability 1 minus p, you delete it. Okay? But in this setting, we can also cook up very different examples, which are not independent. Let's say you could, if you're on a finite graph, you could choose, let's say, uniformly some spanning tree. This would be a random subgraph in my language. And of course, the edges would not be independent because you're forcing it to be a tree. Now, like a family of such examples, or a way to cook up these invariant bond percolations, which will come back in a minute, is the following. So what I call, or which are called factor of IID models. Yes, and these will be important in the sequel, so I want to highlight those. Here we do the following. So for each edge, you consider some uniform element of the interval. Do it independently for all the edges. And then you're allowed to use this information to cook up a random subgraph in a measurable way. So these are all measures which arise as a measurable function, so as a push forward of, let's say, this product. Oh, sorry, I should write the uniform label on 0, 1. Let's say where f is a measurable function from this space 0, 1 to the e to 0, 1 to the e. So the way to think about this, it's a measurable function, so you're allowed to, basically if you are at this edge and you want to decide whether you are in the graph or not, you're allowed to look at the outcome of these labels in some big neighborhood, but in a big finite neighborhood, and then you have to take a call whether you're in it or not, so it's somehow like a local rule. All right. Yeah, please, if at some point I say something which does not make sense, just feel free to interrupt me.
Yeah, sorry, I can't
Yes.
read what you write. P is so F is what?
Yeah, so F is a, yeah, okay, sorry, this did not go well. Let me put it. So I take this space, so just the infinite product space of intervals.
Yeah.
I take a measurable function from this space to subsets of edges.
Okay.
And now in this space, I put IID, uniform labels, and look at a measurable function of that, which will be my factor of IID model.
You want this to be equivariant to?
Not right now, later, yes. So, I mean, let's say an invariant factor of IID model would be one where this map also commutes with the action. Yes.
And then you take the tensor over E, and then what?
So I identify this space with subsets of edges. So
Yeah, but I can't read what's near the.
Uniform. Ah, yeah. So it's just it's the, let's say, Lebesgue measure on 0, 1. So think of this as a uniform element of this interval. Random element. Okay, thank you very much for imploring me to clarify. Okay, great. And if we have these models, some of the interesting questions you can ask, you have now cut some edges, and you can ask, what does this resulting subgraph look like? In particular, if you, let's say, look at 2 points, are they still connected in this random graph? Are there some infinite connected components? If yes, are there many infinite connected components? And these questions turn out to have very deep and fascinating links with the geometry of the graph you are working on. already in this example of Bernoulli percolation, but especially also in the setting where you look at all invariant percolations. So to start off, I want to write a somewhat more formal version of this rough question over there. So problem or question. So describe how the geometry of G, or maybe of the group itself, relates to behavior of invariant percolations. And this goes back to to a very influential work in 1999 of Beniamini, Lyons, Peirce, and Schramm, who showed that this interplay is very fruitful if you look at the property of amenability and non-amenability. So they characterized amenability of the group and used this to prove some very interesting results about also Bernoulli percolation, invariant percolation models in general. It was developed then by many people. So for instance, Damien, who's in the audience, has some interesting results on invariant percolations. But today I want to focus on property T. So I guess I do not have to define property T because it was defined in many talks. So instead I want to start with this theorem. Yeah, so with Mukherjee in 2023. So gamma ST, if and only if the following holds. So there exists a number, P star, which is strictly less than 1. But I mean, it's a number between 0 and 1, and it's somewhere here. So there's an interval to the right of it, such that the following holds. So for every invariant bond percolation mu, distribution of a random subgraph, the following implication is true. So if the infimum over all edges, and then the probability that this edge is in the subgraph is at least P star. Okay, so this looks like I'm requiring something for infinitely many edges, but I'm really just by invariance requiring it to hold around the identity. Then the infimum over all vertices, so all points of the graph, and then the probability that these two are in the same connected component. So this is what I denote by, this is what this event means. There's a random subgraph, and these 2 points are in the same connected component. They're joined by some path which survived, is actually strictly positive. Okay, and this is a genuine infinite condition, because this probability in general would depend on how far away they are. Right? It gets harder to still be connected, but the infimum being positive means there's a uniform lower bound on that. Okay, and I will say a few more words about it in 5 minutes. I will circle back to this and what this really means. First, I want to quickly say something which I cannot go into detail today about, but about the proof of this result, and you can think about what it might mean. So the first thing is this implication. This is due to Russ, Lyons, and Schramm, 99.
Excuse me.
Yes?
Sorry, can you just repeat in words the statement of the theorem?
I see. Okay, I will do it the other. So I wanted to do an in-depth explanation of what it means after I say this, but now I will just do it now. I will just do it now. It's better. Okay, so what does this mean? If you have any invariant bond percolation model, right, you can define this number, and this number just says, look at the identity vertex, has some finite number of edges adjacent to it, and you look at what is the probability that this fixed edge is part of your subgraph, this fixed edge is part of your subgraph, and this fixed edge is part of your subgraph. Look at the infimum. I'm saying I look at all the models where this is at least 1 minus delta, for some uniform delta. And then this local information, so just knowing the ball of radius 1, that you have these, what I call large marginals, is sufficient to tell you that any 2 points, no matter how far away they are actually connected by some path of edges which survived, my deleting edges, with a uniform positive probability. So this is like a very strong version of non-amenability, because if you're on the tree, for instance, so if you look at a tree, it's a non-amenable graph, and this property just fails spectacularly, right? Because if you look at 2 points, and then you want uniformly in their distance, you want them to be connected, then this just means that all these edges must have survived, right? So in fact, you cannot do anything like this. It will be true that you can have, if you just look at, for instance, Bernoulli percolation, then the probability that these 2 points are connected, even as p goes to 1, will just be e to the minus log p and then the distance between them. So there's an exponential decay in the distance. And for property T groups, not only do you not have decay, but actually there's a uniform lower bound. Make sense? Great. So this consequence of property T was first proved by Lyons and Schramm. There's also actually a quantitative version for this.
Question for what you just said, is that a dichotomy, or are there also examples of groups where this decays, let's say,
Yes, there are. So this property, which I described, where you say for all, so for all p, you can find something with marginals p and decay. This is a characterization of amenability, the Hero property, which we also proved in this paper. So I wanted to comment on that in 2 minutes. But there are groups in between. So groups with relative property T, for instance. There are some groups, I think, even which do not have relative property T. So what you would see there is that you cannot do this uniformly, but somehow for each model in some direction it would be unbounded. It would be bounded from below. So here it's all like everywhere, but there's some subtle behavior in between. Further questions? Yes?
So if you restrict to Bernoulli interpolation, is there a characterization of it?
Yeah, great question. So I have some guesses, but I do not. Well, we can talk about it maybe after the talk. Okay? It looks like it should be known and like it's easy to do, but it's surprisingly more subtle than one would think. Actually, the same question came up in my PhD defense, and I've been thinking about. I have some ideas. We can talk about it after the talk. Right. So I just quickly want to mention. So Adrian already had to left, but there's a quantitative version due to Joanna, Tekles, and Sankov from 06, where you can estimate the data in terms of Kazhdan constant and some constant coming from the graph, basically the degree. And what we proved is the other direction. So that if you have this property, then you must be a property T group. In particular, right, this is a property, okay, we're using gamma invariance, but it's a property a priori defined on the Cayley graph. So it's kind of geometric. And what I want to emphasize about this is there's a dynamic characterization of T by Glasner and Weitz in terms of you look at the invariant 0-1 colorings on gamma, and the characterization would say you have T if and only if the set of ergodic measures is closed in the invariant measures, or equivalently not dense. And we did not go through this result, and it's a bit unclear to me whether there's a way to go through this, but we used something else. So in fact, we have an explicit probabilistic construction which builds on some work which starts with Robertson, Steger, or maybe it's with a double E. One E? Correct. From 1908, who studied infinite measure preserving actions of groups with property T. And this was further developed by Chirix, Martin, and Ballet, 04, and Chatterjee, Drutu, Arglund in 2010. For actions of groups on so-called spaces with measured walls, also on some LP spaces. And in particular, you can use this machinery to study also AT minibility, the Hurrow property, and also some quantitative notions, for instance, actions on LP spaces. And our construction, somehow probabilistic construction, which takes as input these works and produces you percolations with which you can work. In particular, we obtain some characterization of the Hurrow property, as well as even of the so-called L1 compression exponent. I want to highlight this, but the non-equivariant one. So, for those of you who know what it is, this, we can talk about it maybe later. It's the important thing is that this is something where you will not have a group action here. You will not look at invariant measures, so it's a bit surprising. But today I want to focus on property T. Right? So I think I already explained what this result is saying. I want to now talk about another way of looking at it. And this is actually the way I prefer. So I already told you this means any 2 points, they're joined with positive probability. So it somehow looks like this random subgraph is extremely well connected. It's an expander-like property, if you wish. And you can make this formal under some additional assumptions on the measure mu. So, yeah, let me put this here. So this condition, inf uv, oh, I should have put, yeah, yes, of mu, and then u is connected to v, being positive is what is called long-range order, or I will abbreviate it as LRO, because somehow the vertices coordinate very well together. And if, let's write it as a theorem, again, Lyons and Schramm from 1999. So if mu is what is known as insertion tolerant, which means that if I just force some edge to be present in my subgraph, it doesn't affect the distribution too much, so it stays absolutely continuous. It's not so important what it means. It's a very natural condition which is satisfied for Bernoulli percolation, for instance. Ergodic, right? And has so-called positive association, which means that if I look at two events which stay true if I add edges, so somehow increasing, monotonically increasing events, then they are positively correlated. So if I have these natural conditions, this is also true for Bernoulli percolation, then long-range order is actually equivalent to saying that mu is supported on configurations where there is a unique infinite cluster. So with probability 1, the subgraph will have many finite clusters, but only one infinite one. Does it make sense? Great. So now. I should have moved it up.
This LRO.
Great. So
there is no invariance assumption here.
Oh, yeah. So yes, so it's invariant. It's somehow implicit in my ergodic definition. But yeah, of course. Or in other words, if you additionally assume these properties, then yeah. Okay. So when you see this, you can wonder about a kind of dual question to this, right? Because this is saying that if you look at a random subgraph with large marginals, so every edge is there with high probability individually, then you are likely to form an infinite cluster, unique infinite cluster, because it's true. It's true for this natural set of measures. Now, the dual question that I was interested in, and I got to it because of this result, is can you also do this in some way at small intensity, so for small marginals, right? Is there some way to cook up a random subgraph, all of where each edge is only there with very small probability, but there's still a unique infinite cluster? And actually, this question, whether you can do it, comes up in a different context, namely in the theory of cost. So I now will go into a small detour, where we'll small intermezzo, and then I will state my second result. All right, so this is part 3, sparse, unique infinite clusters, and already as a somehow teaser, let's say as factor of IID, this will come up as an extra requirement in a minute. So I will start by defining what I just called this somehow dual notion. So fix, let's say, oh no, maybe I will do it consistently. So I say this graph, this Cayley graph, admits sparse, unique, infinite clusters if the following holds. So for every epsilon small, there exists some invariant mu bond population such that the following two hold. On the one hand, if I look at the edges, then each edge is only present with probability at most epsilon. So the graph is very sparse, right? But these few edges coordinate very well, so almost surely there's a unique infinite cluster. Unique connected component. So this is equal to 1. Does it make sense? Great. Maybe I can move it up and I erase some board and then continue. As I already alluded to, this property comes up in measurable group theory, in the notion of cost. So this is kind of a short intermezzo. I do not want to say too much here because there are many people much more qualified to talk about this in the audience. But roughly speaking, so this theory of cost is you can associate to each, to an equivalence relation a number, which measures somehow the weighted average number of generators needed to generate it. And then you can associate to a group its cost, which would be the infemal cost of its three probability measure preserving actions. And if you're interested in when a group has, so first I should say this notion goes back to Levitt and it was developed to a great extent by Damian. If you're interested in whether the group has cost 1, there's a certain probabilistic reduction of that statement. And this goes as follows. Let me write it as a proposition. So if, let's say, still my Cayley graph G has this property, so I should give it a name, probably. Let's call it sparse, unique, infinite cluster. if my Cayley graph has this property, then it follows that the group gamma has cost 1. Okay. And why is this useful? So the theorem I want to mention here is a theorem proved recently by Hutchcroft and Pette in 2020. So if gamma st, then given any Cayley graph, G of gamma, this G has what I call the sparse unique infinite cluster property. Right? So if you combine these two things, you get that Kazhdan groups have cost 1, which they proved and which solved the long-standing open problem of Damien. But I think this property is also very interesting in itself, probabilistically, proving it. Yes, and I will say a few words about the proof in a minute. I just want to, so if you have this theorem in mind and are interested in cost, there's a related question about some of the maximal cost of the group. And if your group has cost 1, which is true for Kazhdan groups, you can ask whether any action has this cost. This would be then called that the group has fixed price 1. And it allows for a similar reduction step, if you're interested in proving that, which says the following. So this is still not known for all property T groups whether they have fixed price 1. And to prove fixed price 1, it is sufficient to prove that G admits so-called factor of IID sparse unique infinite clusters, which just means it's the same property as there, but we're additionally requiring the processes to be equivariant factors of IID labels, of the Bernoulli shift. So let me just write as before, but mu is a gamma equivariant factor of IID. Yeah, and I know that I'm not doing justice to this beautiful field of cost and price. The reason is that I will work mostly with this probabilistic condition. This is what I will be interested in today. I have to be a bit economic with the time, so I want to focus on that really. Because this property, it looks a little bit innocent to additionally require a factor of IID, but it's a genuine extra requirement because a factor map is a local map. And if you inspect this proof, you will see something which is very much not a factor of IID, presumably, so it's not proof, but I can explain it to you in a few minutes. I think I have the time. So they proved this theorem with a somewhat ingenious probabilistic construction where they start, this is your Cayley graph, you start with a Bernoulli percolation with small p, so you just have many finite clusters. And now for each cluster, you flip a coin independently to decide to keep it or delete it. Some of them are kept, some of them are deleted. Now comes the interesting part. You do this 2 times and look at the union of the two things. Okay, this way you have introduced some dependencies between the edges. And if you iterate this construction, they prove that after some finitely many steps, this process will have a unique infinite cluster. Of course, in this process, presumably before you hit the unique cluster, you will be in a position where you have infinitely many infinite clusters. And then this recipe would require you to flip the coin for the infinite cluster, and all of them have 2 coordinates to go out or to stay in. And this is a very much non-local rule. So yeah, it's not really expected that this construction would give you sparse factor of IID. Yes. Also, I should point out there's a very recent proof from a few months ago by, of this theorem by Grabowski, Kazhdan, Sanchez, and Melik, which also generalizes to unimodular random graphs, which have a version of property T that they define. In a sense, they also they don't construct it, but they prove that a certain optimizer must have this property, this sparse unique cluster property. But in their proof, they also use this kind of flipping a coin for an infinite cluster. So really, if you want to do it in a factor of IID manner, this is an extra condition. Okay. Does this make sense so far? Any questions? Right. Yes, one more thing I should say. To appreciate this factor of IID version of the question, if you just think about the most natural factor of IID model, so Bernoulli percolation on a graph, you just delete edges independently. It's very easy to show just by path counting that if P is less than 1 over D minus 1, all the clusters are finite, where D is the degree. Right, so you cannot produce something sparse, unique, infinite like this. Right, and I think this is part of the reason. There's also some other reasons from theory of factor of IID processes that this factor of IID version is of some independent interest in probability theory as well. And I do want to state this question, which goes back implicitly to this work of Hutchcroft and Pette, but was then stated explicitly by Pette and Rokop in a paper from 25. So give interesting non-amenable Cayley graphs examples with this factor of IID sparse, unique, infinite cluster property. Why this disclaimer? So on an amenable group, you do have this property, but it's somehow for the wrong reasons. Because on amenable groups, it's very you can barely produce more than one infinite cluster because of because of amenability. And if you have a non-amenable group where an amenable group sits nicely inside, so somehow like a product, let's say, then you can also produce these things. But what you're really interested in is coming up with a recipe for producing them, which has some chance to work in a general setting. Great. Let me put theorem. So this is with Jan Breivik from 25. So co-compact lattices in, let's say, SL and R have, or their Cayley graphs, all of their Cayley graphs admit these factor of IID sparse, unique, infinite clusters. And more generally, this will be true for co-compact lattices in higher ranked semi-simple groups which have property T. And I will explain the connection very soon, why this comes up. So now I have to mention that the fixed price 1 property for these groups is not new from this result. So this property is new, but not the fixed price. This was proved very recently in a breakthrough of Fraschik, Melik, and Wilkins from 23. And in fact, we build on their result. There's a way to think about our result as a finitary version of theirs. And I will explain that next. So I would say that somehow at least as interesting as this result is actually its method of proof, because it follows from another theorem which is of independent interest in probability, and yeah, I will go into that now if you don't have any questions about this. No? Good.
Sorry, I missed
Yes.
it. What happened to non-compact lattices?
So I don't know. I mean, they have fixed price 1, but I don't know about the factor of IID sparse unique clusters.
What do you expect?
Yes. I somehow, I will explain this, why we only did it for co-compact lattices. But yeah, I mean, definitely for, let's say, SL3Z, I think it's true. I also tried to prove it, but I haven't been able to yet, but. All right, so we will go on a little bit of a tangent, but please bear with me. So I will speak about something now, which is an analog of percolation theory, but in the continuum. And I want to tell you about, say, a new phenomenon for so-called Poisson-Voronoi percolation. Right. Many words, but it's a very simple process. So if we're in a continuum setting, like in RD, the setup of percolation I showed you doesn't really make sense, right? What are the edges that we delete? But there's a natural way to make sense of it. Let me introduce it in general. So consider, let's say, some metric space MD, equipped with some nice infinite measure, say infinite radon measure. It's a nice metric space, locally compact, second countable. And then I define a percolation model as follows. Give me two parameters, lambda and p. So this is just some positive number, and this is between 0 and 1. And I do it in 2 steps. So first step, I throw in a countable random set of points according to a Poisson point process with intensity lambda times mu. So what is this process? If you look at the number of points in 2 disjoint windows, they are independent, and in each window they are distributed according to a Poisson random variable with mean lambda times the measure of that set. So it looks like this. It's just a discretization of our space. And then in the next step, you let each point claim its Voronoi cell, so all the points which are closest to it, closer than to any other point.
So sorry, how do you get this point? How do you start those points?
Yeah, perhaps I should. So these points, this is a countable set of points. It's random, and its distribution is a so-called Poisson point process with intensity measure lambda times mu. So think of this, if you take a set of mu size 1, the expected number of points is lambda in that window. Right. Okay, now I have discretized my space, I can make sense of percolation on it. I just color the cells independently, black or white, with probability p. So this is how this parameter is used. So some of them are colored black, and some of them are colored white. And then I look at the union of the black cells, and I call this thing omega p lambda. It's the union of black cells. Right? And just as in standard percolation theory, I can ask the natural questions about this model. So is there, right? When p is 0, all the cells are white, so there's no big black component. There are no black components. When p is equal to 1, everything is black. And in between, you would see a phase transition where some unbounded black clusters emerge. And I can define these parameters, Pc of lambda to be the smallest p such that the probability that this thing has an unbounded component, connected component, is positive. It's like the critical value, unbounded components emerge, and I can define the uniqueness threshold, which is the same thing, but I'm asking for a unique connected component. It's all the same, but unique. All right, so maybe to warm up, let's think about what happens in Euclidean space. When I change the intensity of the point, then it is just like zooming in or zooming out of the space. So this affects how big the components are, but it doesn't affect whether they are unbounded or not. So in Euclidean space, these numbers, they are equal, and in fact they do not depend on the intensity lambda. And a beautiful result from 06 by Bolobash and Riordan, that if you're in the plane, this number is actually 1/2. Now, if we go to some more general manifolds, this is no longer true. And this goes back to a very influential work of Beniamini and Schramm. So let me write it as a theorem. Beniamini, Schramm, from 2000. So they studied a negatively curved setting, more precisely the hyperbolic plane. And in the hyperbolic plane, because of exponential growth, when lambda gets small, you get these very big cells with many neighbors. So it's easier to produce an unbounded component. So this PC of lambda, the threshold where you start producing infinite things, this converges to 0 as lambda goes to 0. And if we look at PU of lambda, yeah, does someone have a guess what happens to PU? So, to what? To what?
To 1?
It goes to 1, yes. It goes to 1. So this shows you that it's even, I mean, it's a negatively curved space, but it's very hard to produce actually a unique cluster.
That's on the hyperbolic plane?
That's the hyperbolic plane, yes. H2. I didn't write it, sorry. Yes. In H2. Only said it. All right. 10 minutes, very good. So, theorem with Jan Breivik this year. So, let's say if M is the symmetric space of SLNR, or more generally of a higher rank semi-simple Lie group with property T, then the following holds. If we look at this parameter, in the limit as lambda goes to 0, this goes to 0. Okay, so very different from the hyperbolic plane. And in fact, when we first proved this, was a little bit shocking to me. But if you see this, let's move both of them up. Then it now also makes sense how you would obtain this as a corollary, basically, because think about what this says, right? So for any epsilon, there is some lambda such that its PU is smaller than lambda. Okay, so we can look at omega p lambda, where p is bigger than this PU, still smaller than epsilon. This is a model where cells have been colored black with probability p, so its density is p. So it produces a sparse thing which, because you are above the uniqueness threshold, has a unique infinite cluster. And of course, I want it as a factor of IID, but really what you should think of the Poisson, so this model defined here, it's a factor of the Poisson point process. There's like the continuum analog of the Bernoulli shift, so it will also be a factor of IID. So this is the intuition why it holds. In practice, to pull it back onto a particular Cayley graph, we have to require that the lattice is co-compact, at least in the argument that we have. Okay, questions about this result? Then in the final 10 minutes, let me say what is behind the proof of this theorem. Maybe I can erase this one. All right. So one ingredient is actually the theorem that I already erased. This probabilistic consequence of property T, which allows you to update some local information to global. Because what I will tell you about now are some sort of limiting results as lambda goes to 0, which were proved very recently. And we prove a version of this at fixed, but small but fixed lambda. So we use these limiting results, but then, I mean, you have to make them work at small but fixed intensity. For that, we use a version of this first theorem that I showed you. But I guess a crucial ingredient are these limiting results. So this is the final thing I want to mention. So this is about low intensity limits of, and now a word which will look very closely like Poisson-Voronoi percolation, but it's a different word. So of Poisson-Voronoi tessellations. Okay. So in this picture I drew for you of a Voronoi tessellation, right? We have these points, and we form the Voronoi cells. And we can wonder what happens as we send lambda to 0. Okay? In the Euclidean plane, or in Euclidean space, this is just basically zooming into the space. So you just see one cell. And in particular, if you look at this tessellation in the appropriate space, all the limit points will be converges to a trivial tessellation, which consists of one cell, which is the full space. But if you are in a space of exponential growth, this is no longer true. And this was discovered very recently in a series of works, which I will mention over there in 2 minutes, but I first want to sketch what is the mechanism behind it. Because what happens if your space has exponential growth? If you stand in the origin and wonder, does it see more than one cell close to it, then this is not a question of how far away is the first point. This will be the point which claims it. But it's a question of how far away is the first point, and then how far away is the second point, right? Because both have a chance to claim something close to the origin. So both of these points will be contained in some ball, large ball, and conditional on that ball, they are somehow uniform points on that ball. Now, if your space has exponential growth, the size of the boundary of that ball is comparable to the total size, right? It's of the same order. So there's a positive probability, no matter how far away they are, that both the first and the second point are on the sphere. But if they are both on the sphere, then somehow there will be a border close to the origin. And you can make this precise. Okay, I do have to hurry up a little bit. So this was first done in 2019 in a PhD thesis of Bhupati Raju, who proved that as you send lambda goes to 0, there's a unique non-trivial limiting tessellation for regular trees of degree at least 3. A discrete version of what I sketched here. Then he also studied some questions about, like he did not prove the limiting thing, but he studied also this thing in the hyperbolic plane. And this was also studied in 22 by, or used by Buczynski, Curien, Petri, who used this to prove upper bounds on Giga constants of hyperbolic surfaces in large genus. But then it was actually shown that that you can make this precise, so there's a unique non-trivial limiting tessellation in the hyperbolic plane and in general hyperbolic space in 23 by Dachil. So here's some results about H2. Dachil, Curien, Enriquez, Lyons, and Une. So they proved this in any dimension of hyperbolic space d larger than 2. They studied this limiting object and they also gave a general machinery of how to construct this limiting object. But now what is important in our work is what happened shortly after that. It's a paper from 23 of Frascik, Malik, and Wilkins, who used a somewhat different construction from that to study a version of this limiting tessellation for symmetric spaces. And you should think about this limiting tessellation in the following way. So let's say we're in the hyperbolic plane, the points have escaped to infinity, and then there's this infinite cell, there are countably many of them, and sometimes these cells intersect, but some of them might not intersect at all. So it goes here. They proved that if you look at this in higher rank, you actually have a remarkable property which says that the limiting tessellation is as follows. So the IPVT, this is what it's called now, the ideal Poisson-Voronoi tessellation, the limit as lambda goes to 0. In higher rank, satisfies, so it consists of countably many cells, and for any pair of these cells, they intersect somewhere in space, and in fact they intersect along an unbounded region, almost surely. So it is impossible, I think, to imagine in your head what this would look like. But giving, so this result is what enabled them to prove that all lattices in such groups have fixed price 1. And I just quickly, in my final, say, 3 minutes, I just quickly want to sketch how this argument goes, or what the idea behind the argument.
If I may, the talk was 50 minutes.
Sorry?
The talk is 50 minutes, it's not 1 hour.
Yeah, so I'm now perfect on time, right?
Second clock, I
Not
think.
at all.
Ah.
No, actually,
So I thought this is my
it's a
time.
rule that everybody infringes that we should talk 50 minutes in the version.
Okay, so you're saying I actually have more time.
No, you
No, I mean, it's a little,
You are 10 minutes over time.
yeah.
Oh, but
No,
this.
it's fine, it's fine.
Just
we
finish up.
interrupted you
Just
with
finish up.
questions.
Okay, so I had this.
Yeah.
So I had this clock in mind. Then let me not talk about this if you're interested in this. And just the rough ideas, their argument produces some nice process as a factor of this ideal thing. So it goes to a limit. And the way you should think about this result is we build on their result to avoid going to the limit. Okay, so it's at fixed but small lambda. And I'm very sorry for going over time. I thought I'm perfectly on time, and thank you very much for your attention.
So it doesn't happen in rank 1 that they all have unbounded intersection?
No. So it's bounded, the intersection. And in fact, so the Frascik-Malik-Wilkins result says two things which are both crazy, in a sense. So it says that if you look at the neighboring relation of this tessellation, so you declare them neighbors if they have some border, this is a countable complete graph. Right? This is already remarkable. Even more than that, the witnessing of the complete graph property is along some unbounded region. In the hyperbolic plane, for instance, neither is true in a very strong sense. So many of these cells will not touch at all. And if they touch, it's just along some bounded region. And the same in hyperbolic space of any dimension. So yes.
Even in the property T case, the quaternionic hyperbolic spaces?
So this is a very interesting question, which is not known. And I think it's like it's a very suitable test case about to understand what is behind the Frasch-Schickmalik-Wilkins result, whether it's property T or whether it's really the higher rank. And I suspect that it's the higher rank, but still, these rank 1 spaces would be very interesting to know.
Okay, let's thank